symmetrical, right, directional efficiency is limited because they have to be really perfect. So you really need to hit them at a specific angle. Okay, they're really limited. Now, you can actually improve the directional flexibility of these binary gratings by using multi-level binary gratings like that. Okay, so you can use multi-level gratings. So the same thing, but make it multi-level. If you do that, right, you can actually increase the efficiency. Okay, the one with the best efficiency is this one, which we call the blessed gratings, where you have this sawtooth, right? Don't know how to write the saw. So, like you have your is it a hacksaw, things like that. So you get this sawtooth, right? I think you know this one, right? Like I think you've used a hacksaw before. So this one is highly efficient, right? Highly efficient directional coupling, like 100% reflective when metal coated, right? The con is that analog slopes are significantly harder to master or to fabricate, okay? But this is the best one. And then you can actually use these binary gratings in a multi-level grating to actually approach this efficiency, okay? And then we have these slanted gratings, right? So these are highly versatile, right? Spectral and angular bandwidths can be precisely tuned by slanted gratings, okay? So if you slant, then you can actually aim for, so, I mean, from here, you can actually see that the slope and things like that, they affect the efficiency. Remember, we also did this last week where we need to vary the efficiency with spatially, right? From the entrance of the waveguide to the exit, right? And then when we have our eyeballs, like at the out coupler, so we cannot design them uniformly with uniform efficiency because your image will be very bright in the beginning and like at the beginning of the eye box and very dark at the end of the eye box. So you need to vary the efficiency. And one way you can actually vary the efficiency is by doing this design. If you have a slanted grating, maybe the slant decreases with distance, right? Or maybe the height varies and things like that. So key takeaway from this slide is that the shape and the angle and the depth of the grating actually determines the efficiency of the out coupler or the in coupler. That's what you need to take away from this slide. Okay. And then here are actually various real life surface relief gratings that are used in industry. Okay. So you can see we have the binary here. Okay. You can actually see what it looks like when you have an in coupler. Okay, and this is an out coupler. So you can see you can have it as like on the top side, it can be on the bottom side like that, okay? And you can even have it as a multi-stack, right? And for the out coupler, you can see a real life example here. And then we looked at the blazed gratings. So you can see the sawtooth structure here. It can also be at the bottom, right? And it can have a variation where it's sawtooth and then it has a flat surface, okay? And you can actually see an example of the out coupler there, okay? And then the slanted one, you can see here, same thing, right? And you can see even the height here is different from the height, okay? And then it can be also analog grating, okay? Analog as in just has no particular shape, right? So you can have it like that, you can have it like that, so on and so forth. So the angle, the depth, and everything actually affects how much light is reflected out towards the eye, okay, and probably at what end. Okay, so another thing is the power of the nano imprint technology. We looked at this before, right, in previous classes. So if you have these gratings, you can actually use this nanoprint lithography, which we abbreviate as NIL. Okay, and it translates to wafer scale, like it's cheaper and it's actually scalability, so it's easier to manufacture in high volumes, so you can easily mass produce it. Okay, so that's one advantage of this nano imprint lithography. Okay, so these gratings, you can actually use that. So the first thing is mastering, right? You create your mask, so to speak, using e-beam lithography, and then you use stamping to actually create that, and then you cure. Okay, UV curing is actually very important. You see later on, the extent of the UV curing can actually also improve the efficiency or vary the efficiency with time. And then the problem with total internal reflection and this exit pupil expansion is that light is depleted at every single bounce within the waveguide periscope, right? So you have very high or massive brightness at the start of the eye box, and you have negligible brightness at the end of the eye box. And we said last time that you can do that by actually, engineering a varied, not a uniform, efficient outcoupler, but you have to have like structural modulation of the outcoupler. And you can do that by varying the depth. So you can see here the depth varies with distance. So depth equates to efficiency. So you are actually increasing the efficiency with distance. So this will actually help to keep the light uniform in the end. So you can see here, you have massive brightness here and negligible brightness. But if you do this, you see that the brightness is really uniform across the whole eye box. Okay. Okay. So there are many ways to achieve this, but I think you now get the idea. Okay. Now the second problem we talked about this is this chromatic dispersion. Right. We have what are called the ABV numbers, right? So these are typically negative for most diffractive optical elements. Okay. So one way is in the in-coupler, you can have a negative ABV element, and then at the out-coupler, you can have a positive ABV number, and then both will cancel each other. So that's one way you can actually compensate for that. Okay. So this is one challenge that we have. So you can have a compensator like what I just spoke about, right? So you can see that these guys, they are slanting in different directions, right? Okay, so that can actually help to compensate for the chromatic aberration. Okay, so by forcing the in-coupler and out-coupler to operate in exact structural opposites, right? Then the out-coupler will perfectly compensate for the spectral spread impacted by the in-coupler, okay? So that's actually a clever way of taking care of this chromatic aberration. Another problem, we spoke about this briefly at the beginning of the class, is the polarization conversion, right? So you'll find that the optical waveguide is actually optimized for the S polarization, which is the one that's actually the state that is actually orthogonal to the gratings, to the grating lines. Okay, we call that the S state. So at every total internal reflection, you see that the polarization is switched from S to P. Okay, now the P is one that is actually weaker state. Okay, and because the grating lines are optimized for the S, when the light's polarization is switched to P, efficiency is lower. Okay, so you see that most of these waveguides that use total internal reflection, they have very low efficiency. And the main reason for that is this polarization conversion. Okay, and there's a hidden benefit. So I spoke about this in the introduction, right? So you'll find that this time reversal principle, like this altered polarization, it actually prevents the light from being immediately outcoupled by the incoupler. Okay, so light enters here, right, from the display through the incoupler, right? There's also a chance that this light can actually go out through that incoupler immediately. Okay, but because the polarization has been switched from the S state to the P state, light cannot go out through this incoupler. Okay, so that's an added advantage. Okay, so you see that because of that, we don't get this immediate outcoupling of the light via the incoupler. Okay, so it actually allows the light to propagate all the way to the outcoupler. Okay, so it's a hidden advantage, but you need to know that this exists, and this is why most waveguides have very low efficiency. Okay, so in most waveguides, in most cases, we are talking about 10 to 15% efficiency of light. Okay, in most cases. So if you want to have 1,000 nits outside at the outcoupler, you need to have greater than 10,000 nits from your display. If you want 10,000 nits at the end, you need at least 100,000 nits in your display. Okay, that's why you see for most waveguides, we need very high brightness displays. That's where these days you see many people are considering micro LEDs, okay, as the display engine. Okay, because micro LEDs can get all the way to 1 million nits, right? It is really that bright. Okay, so we need that. So this is just the loss in the waveguide. You have losses everywhere else. Remember, we were talking about losses in the pancake optics, in all these places, right? So you get a lot of losses. So you need to start with a very bright display so that you actually get something bright in the end. I hope this is very clear. If you have a question, feel free to interrupt me. I just want to go through this and finish so that we have 44 slides today, so that we can finish early and then break at once. Do you want a break, or you want me to continue and just finish the slides? If you want a short break, raise your hand. You want a break? Okay, so let's come back after 10 minutes. Okay, take a short break and then we come back. You want a break, right? So let's come back at 2:15 and then we can go through the other 20 slides. Let's come back at 2:15. Okay. Which is in your case, it's going to be what? 4:15, right? Not 2:15. Hope I'm correct. 4:15. Okay, so we'll see you then.
Recording stopped. Recording in progress.
Hello. Are we all back? Okay, good. Can you see the screen now? Okay, good. Okay, let's quickly finish. Okay, so I think any questions so far? Questions? Okay, good. Okay, now this is actually a figure that illustrates how some of the surface relief gratings are being applied in actual waveguide combiners. And an example here is the HoloLens V1. Okay, so you can see like the very much things that I really need you to understand. So in most cases, if you have very small displays, because sometimes it's not easy. But I explained this before. So if I have a display, right? So in many cases, a display is made up of the driving or the backplane, right? Call it the backplane. Okay, we have the backplane of the display. So the backplane is where you have all your switches, right? Your switches and your drivers. Okay. And if this is on glass, if it is on most displays, you have your TFTs. You can have your switching TFTs and your driving TFTs. Okay. And then you have the emissive device, the emissive part. Okay. And this can be liquid crystal, it can be OLED, right? It can be OLED. My writing is really bad here. Let's see. Sorry about that. Okay. So this can be liquid crystal. This can be OLED, right? Or it can actually be maybe LEDs. And in this technology, because we are using very, very small displays, this would be a micro OLED, and this would be micro LED. And the LC would be maybe LC on silicon, right? In most cases. So, but the common thing that if you see is that you have two, you always have the backplane and you always have the emissive device. Now, my point here, what I'm trying to get at is maybe except for the LCO OS, the liquid crystal and silicon, for OLED and micro LED, it's very hard to have side-by-side RGB. Okay, so it's hard to get RGB pixels side by side. So in most cases, we use white OLED and we've used color filters. But you see that doing that actually also complicates. So if it is very, very small and very high PPI, even the color filters to pattern them in such a way that they are actually very small is really hard to do. So in many cases for these very small displays for AR optics, we have 3 separate displays. You have your red, green, and blue. These are actually separate displays. Okay, display for red, one small display for blue, and one small display for green. Okay, manufacturing, that's easier. Okay, because it's really hard to make a full color micro display. Okay, so a monochrome display can be made, and we have these 3 separate displays. And that's what you can see here. So if you look at this diagram here, right, you can see that you have 2 waveguide optics. You have this one and you have that one. Okay, so ideally we have a 3rd one here. Okay, so let's just say this is for R, this is for G, this is for B. Okay, that's the way it is. And then in this particular example here, it looks like the display is actually full color in a way, okay? And then the waveguide optics or the in-couplers, they are designed in such a way that the first one will only reflect or diffract depending on the tech, right? It will only diffract red, okay? And then green and blue passes through without any absorption or anything, okay? And then the second one will only diffract green, okay? And then the last one is optimized for diffraction blue. Does that make sense? Okay, so you have this channel for every color. And then you see in the next example, you can see that you actually have different colors to begin with. So maybe this could be the example of what I'm telling you, that you actually have separate displays for RGB. Okay, and then each is directed to each channel, to the respective channel. Okay, does that make sense? Okay, so you have 3 separate displays and you have 3 channels, okay, for each color. Or you can have a full color display, and then your optics are designed in such a way that they are optimized. Each channel is optimized for each color. You have this transparency for different colors. Does that make sense? Okay, so that's what I wanted you to understand. So I copied this text from the textbook. I thought this is very important for you, maybe to put everything together. So let's just read through so that we understand, right? So the display engine is located on the opposite side of the eye box. So your eye box is going to be here, right? So your display is located here, okay? And then the single input pupil carries the entire image over the various colors, right? So that's what I said, that this is a full color display or full color image coming in, okay? And then the in-couplers have been chosen to be slanted gratings for their ability to act as on a specific spectral range, okay? So depending on the slant, the depth and everything, the in-coupler can actually be selected to a specific spectral range, okay? And then at the same time, it lets the remaining spectrum unaffected in the 0 order to be processed by the next in-coupler. So if this is for red, only red here is going to be processed. and then everything else is transparent. And at the second level, you have green, and everything else goes through. Okay, so such uncoated slanted gratings work both in transmission and reflection mode, but can be optimized to work more efficiently in a specific mode. So this is the in couplers here. Okay, and then if you now look at the out coupler here on the other side, you can see that they also have slanted gratings, right? So this can also be tuned effectively over a specific incoming angular range and leave the see-through field quasi unaffected. Okay, so you remember you still have light from the environment coming through. And the other thing you can see is that the part of the see-through field that is indeed diffracted by the outcouplers is trapped by total internal reflection and does not make it into the eye box. Remember, most of these, they are 50-50%, right? 50% goes through and 50% is absorbed or reflected somehow. And then another thing that you need to see is that the efficiency, the depth of the gratings also vary with distance or in space across the eye box so that you have uniform luminance, okay? So this sort of like sums up what we've been looking at, okay? And then another thing is that the redirection gratings are not shown here, right? Input and output gratings slants are set close to 45 degrees, and the direction gratings slant at half this angle. The periods of the gratings are tuned in each guide to produce the right total internal reflection for the entire FOV for specific color, okay? And this enables us to have the same central diffraction angle in each guide for each RGB LED color band, okay? So this is really, really important. If you read through this and if there's something that you still don't understand, please let me know, okay? So that's one architecture here where you have like a full color image coming in, okay? So this is the second one. So in this architecture here, we actually have the display engine located on the same side of the eye box. So your eye box is here, the display is located on the same side. The input pupils are specially color demultiplexed, right? It means you just have different colors coming in, right? It could be separate displays, or maybe somehow you can demultiplex the colors just as they exit the display. Okay. And here we're just showing two colors, right? So the specially demultiplexed colors can be done conveniently with a color sequential LC display mode, for which the illumination LEDs are also specially demultiplexed, or it can be separate displays altogether. So in this configuration, the input gratings couplers are stronger blessed gratings, okay, coated with a reflective metal, such as aluminum. They do not need to work over a specific single color's spectral width, since the colors are already demultiplexed, so that decreases complexity. And then if we look at the out couplers, right, these are also simple top-down binary gratings. Okay, so top-down binary gratings, which are also depth modulators to produce uniform eye box for the user. So you can see the depth is modulated for that uniform, right? So these binary gratings are shallow, acting very little on the see-through, but they have much stronger efficiency when working in internal reflection diffraction mode, since the optical path length in this case is longer by a factor of 2n cos alpha. Okay, so read through this, just see if you understand everything. But just that's the whole idea, right? You have a separate channel for each color, and you can do that from a full color display, or you can have that from separate channels altogether. Okay, so now let's look at the power of this SRG architecture. So the power is that massively scalable, right? And we can use this NIL. And we are actually, I think now people can actually do Gen 2 plus. Limitless topological design freedom. You can have pairs, binary, slanted, and multi-layered, right? Ultra thin, lightweight form factors. I think you can guess that, right? And then the cost or the penalty that you get for getting all this, okay, is that highly dispersive. So highly dispersive negative ABV number. So it requires symmetric metric coupling. Okay, so you have negative in the in coupler and positive in the out coupler. The total internal reflection depletion, right? So this requires maybe depth modulation of that uniform brightness. And then you have that polarization conversion, okay, from S states to P states, which drastically decreases the efficiency. Okay, so you really need to balance that, the S and the P states, to actually get a good result in the end. Okay, so that's all for surface relief gratings. Now we move to holographic, like volume holographic optical elements, VOHEs. Okay. So the VOHEs use recorded interference patterns in the photopolymers. So unlike the SRGs, which rely on physical surface nanostructures, the VOH relies on an index of reflection swing within the volume of the material itself. Okay, so the volume of the material will actually result in this refraction, index of refraction swing. So swing is just more like a change, right? So if the index of refraction changes, then the light can actually maybe cannot reach that critical angle, right? And then it escapes the waveguide. That's how you get that EPE. Okay, so
Professor, a question.
Yes.
Regarding this VHOE, so the index of refraction is changing in a single material, yeah? Am I?
Yeah. Yes.
Right?
So that material has a different refractive index, and you can actually tune it to get uniform brightness. Okay. So maybe when you cure the material or you do other things, you can actually tune it specially so that you actually get that you can control the refractive index with distance. I don't know if that was your question. Was that your question? Okay, good. So you can actually tune the refractive in these photopolymers. Now, these are VHOEs. We can categorize them by thickness, right? So we have the thin VHOEs, which have a thickness that ranges from 2 to 70 microns, or we can have the thick ones, which have a thickness ranging from 100 to 500 microns. And then the materials for the thin ones are photopolymers, okay? And then for the thick ones, we use thick photopolymers. So these are the examples of the companies that are actually using thick. And here the example of companies that are actually using the thin VHOEs as of 2021, I guess. In terms of characteristics, the thin ones have high efficiency in specific modes, replicated rapidly via continuous row-to-row processing. So if they are thin, you can easily manufacture them because these are polymers, right? They can be printed or they can be manufactured by row-to-row processes. And then for the thick ones, hundreds of phase multiplexed break conditions, right? Which require extremely high spectral control and automated successive multi-exposure setups. So they're a bit complex in a way. So these are the examples. So the standard, and then these are the diligence, right? As examples, right? So the whole idea is you need to break the, for example, if you have an outcap at the outcap coupling stage, right? You need to break the total internal condition. Okay. So the index swing is actually the is actually the mechanism that allows light to successfully escape this total internal reflection trap. So when light trapped by TRR passes this VHOEs, right? These are volume holographic elements. They can actually switch from an off break condition to an on break condition. So the on break condition is the one that will actually allow it to escape. And then here you actually have a real life example, right, of these VHOEs. You can see here that for a thin transmission, so this is the HPDLC and the diligence, the thickness is around 2 to 3 microns. Okay, and you can see it's around here, right? And then for the thick ones, they're still thin, right? If it's below 70, I guess, that's still thin, or below 100. What was the definition here? Yeah, 2 to 70. But let's just say below 100 is still in the thin. So here you have, these are the companies that are actually doing this. So you have this photopolymer. And then the thick ones, you can see what they look like here. They are around 100 to 500 microns, okay? And Arconia and Apple used them before. Another thing that you really need to know here is that for the thin ones, they can actually be sandwiched, right? Or they can actually be coated at the base or top of the waveguide. Okay, so let's read through these notes. I put these here for you so that you can really grasp the concept. Okay. So the top part of the figure, right? It shows 1D EPE. You can clearly see by these arrows here. So that's how you are expanding the eye box. Okay. And then when the field traverses the hologram downwards, it is in the off-break condition. So I mentioned this before. And when it traverses the volume hologram upwards after the TRR reflection, it is in an on-break condition or close to it. And then this actually creates a weak or strong diffracted beam that breaks the TRI condition. Okay, so you have that index of refraction swing, and that will actually affect the angle at which the light is going to hit a waveguide, and then it can actually escape. So a hologram sandwiched between plates might look more complex or produce complex to produce than a reflective or transmission laminated version, but it has the advantage of or the advantage that it can operate in both transmission and reflection, as you can see here. Okay, so that's our volume holograms here. And then by expanding the material volume to around 500 microns, engineers can actually phase multiplex hundreds of individual holograms into a single substrate. And multiple break conditions work in concert to build a wider systematic angular bandwidth. So you might need all these maybe to vary the efficiency so that you have a uniform brightness, or you can actually do that for other things. Okay. So now if you look at this diagram here, you can see that the core problem, right, that we talked about, the achromatic bottleneck, right? So a standard diffractive surface grating, the standard surface gratings and volumetric holograms inherently possess that negative ABV number, right? Remember previously in the previous ones, because we had these settings, right? We could do like a negative one, and at the in-coupler, we do a positive one, right? So that's how we compensated, okay? But for the VO, what you call them, the volume holograms, we also need to do a similar thing, okay? So you can see that the consequence, right, for the previous one is that to achieve a more than 50 plus degree of FOV, 50 plus degrees of FOV without catastrophic color separation, right? The industry is forced to abandon single layer architectures and stack multiple plates RGB waveguides. So we could do this easily for the gratings that we did before, but when we now have these polymeric layers like this, the only way we can actually compensate for that is to have these multiple layers together, as you can see here. So if we have these multiple layers, if we stack them, right, like that, then we can have like a waveguide for each color, right? And that will actually help reduce that chromatic aberration. If you stack them like that, as we discussed in these examples here, you have separate channels for each color. That will actually help solve for that. And then another thing that we have beyond holography is resonant waveguide gratings, right? So these are just submicron dielectric structures that utilize electron leaky guided modes, okay? The advantage is that they are extremely high degree of optical tuning. So by optical tuning, we mean wavelength, phase, and polarization are integrated directly on top of the substrate. So you can use these resonant waveguide gratings by using these thin dielectric materials, and you put them on top of the waveguide, right? But most of these are still not really very much adopted, right? For example, here we have an example of the resonant waveguide grating, right? That is on top of our combiner. So we have our in coupler here, and we have our out coupler here. Okay, and then you can see that because these are dielectrics, right? You can actually print them by row-to-row replication. Okay, and the company CSAM Research Center in Switzerland, they actually developed these in the 1980s, but their adoption has not been very, very widely seen so far. Okay, and then the last thing that we are going to look at are metasurfaces. Okay, so metasurfaces are like the holy grail, but still, they are still at an early phase. So the concept is that you have these binary nanostructures acting as sub-wavelength resonators instantly imprinted right on top of your waveguide, right? And you can see an example here. So you get all these nanostructures, these metasurface imprints, so to speak, right? And if you do that, you can actually be able to design very complex reflective or diffractive functions in an absolutely flat 2D layer without volumetric thickness. Okay, so that's one key advantage to this metasurface imprint technology. And this sort of like sums everything up. So we have the dispersive couplers, we have the pure achromatic, we have phase multiplex, and we have the engineered pseudo achromatic couplers. Okay, so for the dispersive couplers, we looked at the surface relief gratings, and we had the VHOEs, right? And then for the pure achromatic, where the partial mirrors, right? And then for the phase multiplexed, we had these thick VHOEs. And then finally, we have these multi-surfaces for an ultimate flat form factor, okay? And then here you can actually see an image from your book where we have the actual designs, dispersive, where we have our refractives and diffractives, right? And then we have our pure achromatic. So we have our mirrors, okay? And then we have the engineered pseudo achromatic couplers. So this is where we have our holographics and our metasurfaces, okay? So this is, in summary, what we have been looking at. You can read through here and then see if you understood everything. Okay, so just for insights, so the entire evolution from the surface gratings to thick holograms to sub-wavelength metasurfaces is driven by a single engineering goal, right? Collapsing the three-plate RGB stack into one flawless piece of glass. And the impact is to reduce weight, right? And eliminates submicron lithographic alignment errors between plates and radically lowers consumer cost. So instead of having these bulky 3 plates, one for each channel. Our goal is to, you know, flatten everything into a small thing. And we can achieve that by meta surfaces, but we are still a long way until we get to that point. But this is our ultimate goal. Okay. So we always have this this reality where we always need to choose between complexity, or to choose between scale and yield, right? So photopolymers are uniquely suited for continuous row to row. So if we use photopolymers, you can do this row to row manufacturing, right? Nanostructures like the SRGs, right? And metasurfaces require IC level, wafer scale, nano imprint, lithography using high index spin on glass. Okay, so that's so here scalability is very, very high. But if we want good accuracy and things like that, we need to go to nanostructures. Okay, and it's always a trade-off between scale and yield. Okay, and then we have this fix for uniformity. I think we spoke about this in detail before. And then I think the roadmap is towards metasurfaces, right? That will actually unlock a lot of engineering benefits, right? And then the hurdle is always manufacturing and cost. We need to find a way that we can actually scale so that we can reduce cost. And then in this slide here, you have everything all together, summarizing all the waveguide coupler tech that we looked at, right? And the different characteristics, okay? Like operation, effective coupling, transmission coupling, efficiency modulation, and so on and so forth. So you can go through this at your own time. And then if you don't understand something, you can then go back to the notes or the book to understand. Excuse me, I'm losing my voice. And then here we have the summary of all the devices that we looked at. Okay, so that's all for today. I wanted to leave some time for you guys to ask me any questions if you have any. But this is the end of our course. I hope it helped you to understand optics or AR, VR devices a little bit. I know some of you or most of you are not in that field, but I hope next time you see someone wearing AR glasses or VR headset, you understand the complexity of making them, right? Or if you listen to a talk on AR, VR optics, I hope some of these, if someone talks about F4V, if someone talks about MTF, things like that, I hope it's going to make sense to you, right? The iBox, the iBox expansion, right? Things like that. I hope you took away one or two concepts from this class, which is the whole purpose of the class. Okay? Any questions? This is our last day together. See you next week. Maybe I won't be able to see you because the exam is in person, right? Okay. Anyway, good luck. And good luck in other exams as well. We will see each other maybe at SID or another class. I don't know. The display industry is very small. We'll definitely meet one way or the other. Okay. Or maybe I'll visit you guys. I'll see you in Korea at some point. Okay. So if you don't have any questions, it was very nice meeting you all and spending these 15 weeks together. Wish you all the best in your courses, in everything you do. Okay, if you have any questions, feel free to text me. You have my number, you have my email. I'm always happy to answer any questions, even things that don't have to do with this class. Okay. 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 Bye-bye.
Thank you, Professor.
Okay.
Thank you, Professor.
Okay.
Thank you.
Bye-bye. Bye.
Bye.